So in this video, I want to take a look at using the Altmon monitor to test the RAM cards for my Altair 8800 build. So here we're looking at a picture of the cards that are currently in the system. We have the CPU card up front here. This is the reproduction card that we built in a previous video with the 8080 processor in it. We have the front panel interface here for the MSI-Gs, the Altair front panel over here. Currently the ribbon cable is disconnected. We have two Godbout, however you say it, EconoRAM 4 cards in here. Each one's a 16K card. This card's at address 0000 to 3FFFF. This one at 4000 to 7FFFF. And then I have what I believe to be a good card here. This is one of my Memory Merchant 16K cards, and this one's at address 800 to CFFF, and I need memory starting at to BFFF. I need memory starting at address BFFF and down to act as the stack for the Altmon monitor. So there has to be, and probably 256 bytes would be enough of good RAM at the address that monitor expects to find RAM for the stack. We have the MITS SIOB card here that we've configured to be our TTY0 port. And we looked at this card previously. The blue card here is the RS-232 level converters. We did some wiring changes on it to get the proper signals out for transmit buffer ready to send, etc. And finally in the back was the FDC Plus floppy controller. We looked at this in an early video. This card emulates the original Altair 8-inch floppy controller. It can control 8-inch and 5 1/4 drives, etc. And of course, there's a cable off here to the drives. This board also can provide 64K of RAM and ROM. And right now, the board is strapped to say I'm not supplying any RAM at all, but it is supplying the Altmon monitor at address F800 and up. So really, that's the configuration. We're running Altmon off this card here. We've got 3 RAM cards. We want to test these front 2 ones here. So let's take a look at the memory map of the machine. We just kind of talk through this again, but we've got the 2 Godbout cards here in these address blocks. We've got that Memory Merchant card. The stack for Altmon starts at BFFF, and remember, stacks grow downward, so it starts at the top of this address space and grows downward. We have an empty memory block, and we have 2K of ROM in the memory map with these entry points. F800 is the Altmon we'll be using, Intel hex loader, etc., and finally the combined disk bootloader we're using to boot the machine. I believe I had one other picture here. This is some documentation on the Altmon monitor. It's based on a monitor from Vector Graphics, so it's historically correct. It's got a number of commands here, and the command we're going to use is this test command that tests memory. This is a destructive test. There's also a non-destructive test. In this case, I don't care. I want to test memory on those cards and see what we've got. It's a capable little monitor. While we're here, actually, oops, let me blow this up a bit. The font's kind of small. I want to look at the source code for Altmon while we're here. So a nice comment block. We're going to look at the source code because ultimately, if I can find the entries here, stack pointer is defined to start at C000 and grow down from there. And the card I've got in goes through BFFF. There's actually not a byte of memory at C000, but the board seems to run just fine. It's really the top of stack apparently doesn't have to have a byte of memory, is my guess why this works. There may have been a comment in here about this. Maybe not. It may have been elsewhere, where this is really defined to be the amount of memory you have in the machine. Anyhow, if we could change the origin of the code. We could move the stack pointer it expects to find. If I only had 16K in the machine, I would need to lower this down to where the top of that 16K was. Could actually patch the code in the monitor ROM if we really wanted to do that, but that's the Altmon. So really the thing to do here is let's get on the machine and actually test some memory. So let me get TerraTerm opened here. So let's get back and look at the memory map while we're doing this. I will move over here and power the machine up. Reset it, examine F800 and run it. It should start Altmon, and it did. So let's poke at a couple things here. If we do test, I'm going to hit this empty block up here from C000 to C00F, just those 16 bytes. We should see exactly what we're seeing here. Let me stop this and start Altmon again. And so what we're seeing here, of course this just loops and loops and loops, is we're reading back FF. So this looks like it's walking ones kind of through the memory space. But you can see here it's failing because it's finding FFFF, so it doesn't match what it's trying to write. And let me start up Altmon again because it got messed up there when I cycled the power. If we test 0000 to 000F, this is passing. Every time a period's printed, it means that it's done one full test pass. So this is what, that's only 16 bytes, but what it looks like in memory when it's actually working. Let me get control of the machine back here. I now want to test the lower 16 bytes of this card here just to see what we get. So we're going to test from 4000 to 400F. And we immediately see there's errors. I kind of expected that. Get the monitor started again. Stop, reset, examine, run. So let's kind of look at the bit pattern here for the failures. It's an interesting, so it wrote a 3B and it read back a 7B. So that says there may be a bit stuck high, but notice it's not every address. Of course, there's addresses where it's writing zeros. This is B. It's looking to me like the bit 6 may be stuck high here. This is kind of curious. Let's look at this in a bit more detail. We'll fire up Notepad here. Let's just take one of these. We wrote an A9, and we and we got back an E9. So we wrote a 8A9, and we read back an E9. Oops. So we can see right here this bit looks like it might be stuck. 1B, 5B, 1, oops. 1, 8, 9AB, and we got back a 5, oops. We got back a 5B. This is really looking to me like data bit 6 here. Remember, it's data 0 to data 7. Data bit 6 seems to be stuck at a 1, which is interesting. And that seems to be, and remember, the bit weight of this is 4. So 3 plus 4 becomes 7. 8 plus 4 becomes C. 0 plus 4 becomes 4. Really, for the bytes that failed here, that's looking pretty conclusive to me that that is potentially an issue with this card. So what we looked at was really only the bottom 16 bytes on the cards. And there's 4 banks of RAM chips on here. There's 32 total RAM chips. So let's think about this and test some of the other banks. 7FFF. So the card lives in this address space. So really the card's going to go from 4th to, what, 4FFF, 5 to 5FFF for second bank, 6 to 6FFF, and 7 to 7FFF. So like I said, there's 4 banks on the card. Each one is 4K, so this would be the memory addresses for the banks. Let's test the next bank of chips up. So that's 5000 to 5FFF. So test 5000 hex to 5, and we're just going to test it for 16 bytes again. And that would tend to say that block is good. I'm going to stop the machine in, again reset it, and get Altmon back. So what we saw here was this looked like it was, at least for those lower 16 bytes, good. Let's test the first 16 bytes of this block. Test 6000 to 600F. And again, the first 16 bytes of that block look like they're probably good. Goof. Let me get control of the machine back again. I'm not sure why I can't interrupt the memory test, but I can't. Test 7FFF. I'm actually testing that entire bank here, is why that's running slower, and that looks fine as well. So I actually want to go back and do the full set of bytes on both of those banks. Stop the machine, reset it, examine F800. So let's go ahead and test 5000 to 5FFF. So I think we're pretty conclusively here determining that we've got a bad RAM chip in that first block. Remember, each time a period's printed, it's fully tested. That address space we defined. And let's test 4000. No, we want to test. We've tested 7 and 5, 6000 to 6FFF hex. Again, that looks good. Reset, examine, run. And let's test the top 16 bytes here, and the bank we believe is bad. So we're going to test 3FF0 to 3FFF. And it looks like the top 16 bytes here are okay. I wish, oh, escape gets me out. I didn't realize that. Thank you. Test 000 0 to 000F. This I'm testing on what we believe is a good RAM card. So I've just gone to the wrong address block. That's my bad. You need to test 4FF0 to 4FFF. This gets back to where we were seeing the errors originally, and we still see the errors. And this is a case where escape doesn't seem to want to get me out. Okay, so I'm not crazy. I need to close out Altmon here, or Terraterm, because it got screwed up. So let's look at the top 16 bytes in here now. So test 4FF0 to 4FFF. I'll go ahead and stop. I think this is pretty conclusive. So we've got a bad RAM chip in it, and it's really the one we determined right here. It's on data bit 6. So we're looking at the schematic for the card here. This is for the Goodbot card, and it's really a pretty simple schematic. We've got A0 to A11 coming onto the card, and they're buffered. become the MA0 to 11 signals on the card. We've got data out off the bus, which is buffered, becoming what they call memory data in. That seems kind of backwards to me. Yeah, that is the S100 bus numbers. And memory data out on the card. That's correct. Out from the processor, going into the card to write to the RAM. And out from the card, going to the data in bus for the processor. The issue seems to be on this bit right here. Remember, we're seeing 4 added to that upper nibble every time. And this would be bit weight 1248 for the lower nibble, 1248 for the upper. So we suspect it's MD06. If we look at A14 and 15, those go to a 2 to 4 demux. And when they're both zeros, this Y0 is going to become active. It's going to come low. And enable the card. This is where we can disable individual 1K blocks on the card. I've got these switches all closed at this point on the card. That enables the card. Then we've got another 2 to 4 demux. So chip enables 0 is going to be the least significant bank, or the Y0 output. If these are 0, 0, that one's going to be a 0. If these are 0, 1, it's going to be Y1, 1, 0, Y2, and 1, 1, Y3. So it really is Y0. It seems to respect phantom. Write enable switches. We know we're able to write to the card. So really, I understand this part of the schematic. It's very straightforward. And then we've got the details on the memory itself. Looking at the power supply here, I'm going to assume the power supply rails are good. I should measure them. I say that because we don't have a full bank or the full card failing. There are 37805 regulators, it looks like, powering different parts of the card. We've kind of got a block diagram of how this works. But really, the tell is right here. So memory data 6, bit 6 is what's failing, and it's failing in that chip enable 0 block. And that says to me device A6 on the board. I'm assuming the board's going to be labeled A6 is going to be the part that we suspect is bad. So I'll pull the board here and maybe swap that with a different part and see if we can make the issue move. So let me get to the photo of the cards here, and I'll tell you what I've just done, if I can find them. So this is the card itself. I pulled it from the machine. This is the chip we suspect is bad. I've already pulled these two out of the sockets, and they're just sitting here. That's why they look funny. If we take a close-up at the card, we can see here the ABCD and the 765 and A6. We suspected with this chip. So what I've done is I've taken the chip we suspect is bad, A6, and I've swapped it up here to A7 and taken this chip and swapped it down. And this is really pretty cool because this little map here really does represent the layout of the chips on the board. A couple of things to say here is because it was a single bit issue in this chip and it didn't occur in these devices, that tends to make me believe that these data buffers here, if this data buffer was bad, for 6 we would have seen 1s or 0s for every address on the board, and we didn't. So that tended to rule out this particular guy right here being the problem. The fact that the other 4 banks, B, C, and D, seem to be okay. I mean, we were able to fully test each one of the banks, and it was fine. Again, leads me away from this being, something common being the issue. I don't know how the power is exactly distributed across the chips. I don't see any indication here that really tells me that. I don't see an indication that really tells me how the power is distributed across all the chips, but I don't really suspect a power issue. So really, we've swapped the 2 chips. Too many photos here. We've swapped the 2 chips. We should now see the failure at A7. Let's get back to TerraTerm. Let me actually restart TerraTerm. It's got a garbage character on it. Let me bring the machine back up and reset, examine, run. Let me hop back here to our notes. Actually, the notes are in Notepad++. There's our notes. TerraTerm back. And I suspect now if we test 4000 to 400F, we'll see the issue being in the most significant bit. And again, I can't break out of that. So let me stop. Let's analyze what we're seeing. So we expected a 1 and we read a 9. So let's analyze that. We expected a 1A and we read a 9A if I remember correctly. 1A and we read a 9A. And that would be 0001, 1010, and 1001, and 1010. So that indicates the error is now on this bit 7 here, whereas before it was on bit 6, which supports the chip we moved being the issue. If we take a different bit pattern, 7F and FF, that'll be easy. 7F and FF. I can't type here. 7F, F. You can see again that this bit seems to be the bit that's bad. So we swapped the two chips in this bank that represent data 6 and data 7. The issue has followed that chip from bit 6 up to bit 7. So we've identified the bad chip here, which is really pretty nice. So the chip I currently have right here at A7 is the issue. The question becomes, can I find another one of these in my stock? I don't honestly know. I'll have to look, but in the end, this kind of takes you through the process that was used to identify the bad device. Using the Altmon monitor, looking at the address space of the machine. You can kind of recap here. Cards we talked about in the machine, 0 to 3FFF, 400 to 7FFF. What we believe is a good card to provide stack space from BFFF down for the Altmon. Altmon ROM is running off this card back here, our serial card, our processor and front panel. We're testing in this address space, really just looking at the bottom 16 bytes down here, but we see the issue. We've looked at the schematic and really determined in the end this chip here, which we swapped. We're confident that it's not any of the common logic here. All 4 of the blocks seem to be being selected. There could be other more subtle issues here, but they would cause something different from what we're actually seeing. Really, I think that covers it. So I'll look for a replacement chip. And we'll see you in the next video.